Can you imagine if we could successfully send a spacecraft to another star system, that we could take pictures of a world orbiting around another star up close? Search for alien life, try to just understand what's going on other exoplanets. Well, the problem is that these other star systems are so far away, and for us to send a spacecraft at the kinds of velocities that we're capable of will take centuries, millennia. There's got to be a faster way. Unfortunately, the tyranny of the rocket equation says that you have to use the most compact fuel sources that are out there, pretty much antimatter, and it has problems of its own. Or you use some kind of beamed propulsion where you send your power or your propulsion from some external satellite to accelerate your spacecraft up to the high velocity. You're probably familiar with breakthrough starshot, where you would use a laser to send a tiny spacecraft to high velocities to complete that journey. What if there was a way to send a larger, more Voyager-like spacecraft at that kind of velocity? My guest today is Jeff Greason. He's the chief technologist of Electric Sky, and he's the chairman of the Tau Zero Foundation. And he has been working on an idea to send a spacecraft at high speeds between our star systems using a beamed propulsion system. You would fly a satellite close to the sun, and it would just hover there, harvesting the enormous amounts of energy, and then beam that at a spacecraft to accelerate it to high velocities. There's a lot of interesting sort of intricacies to this concept. We discuss that, as well as the risks, how it compares to other ideas. And one of the most fascinating ideas is how you could actually have a multi-staged interstellar spacecraft concept. So enjoy this fascinating conversation about interstellar travel with Jeff Greason. Jeff, help me understand first, what is a statite? I've heard this term before, but I haven't actually done a lot of digging into it. What are statites?
It's short for stationary satellite, and it's a thing that hovers over a point. People have talked about doing that on the Earth with long duration balloons that do station keeping, or unmanned aerial vehicles that circle around a point. People have talked about doing it over the Earth's poles using magnetic fields. And, the paper we're going to talk about today is hovering over a point near the sun using the solar wind pressure from the sun to offset the sun's gravity.
Right. So, I guess the classic example would be like a geostationary satellite, in that it is from a person on the ground. It seems to be hovering in this fixed point in the sky, but in this case, using orbital mechanics to do your balancing for you. But there are other ways that you could balance.
Yeah, because it does use orbital mechanics, it's not usually thought of as the same thing. But in terms of what the applications are like, yeah, it kind of does the same job.
Right. You're trying to get the results of a geostationary satellite in places that aren't geostationary orbit.
Correct.
Using other forces to balance out the gravity that is going to be acting on whatever it is that you're trying to hover.
Exactly.
Right. Okay. And so, you talked about a bunch. Each one, I think, is a conversation and a series of research papers all on its own. But let's talk about sun-based statites. So what are the balance of forces that are working on a satellite that it's attempt to hover in space above the sun?
Well, basically, if you're not in solar orbit and you're close to the sun, the gravity is pretty fierce. A couple meter per second squared, even at 0.04, 0.05 AU. But conversely, the solar wind is dense in close to the sun. And, without taking too long to get into it, the manner in which the solar wind is accelerated by the sun takes a little bit of distance to take place. But by 0.04, 0.05 AU, it's transitioned to supersonic flow. So you have some force to grab onto there. It's still pretty fluffy, so you need to grab onto it with fields that have reasonable spatial extents rather than matter. You can't just put up a physical sail, because you would never be the weight of the sail. The pressure of the sail would not be enough to offset the weight of the sail. Whereas but the solar wind is made up of charged particles, they can be deflected by electric and magnetic fields. So it's in principle possible to deflect a large enough cross-sectional area of the wind to offset the weight of a spacecraft.
And I've reported on these ideas in the past. I know there's a group in Finland that is working on electric sails. People have proposed mag sails, that instead of a solar sail that everyone's really familiar with, a big sheet of mylar that's floating, you're running wires and you're running electricity through them, and then that is interacting with the solar wind, and that's giving you that offsetting force that's pulling in. So like the mylar idea is right out. You'd have to get too close to the sun for it to remain in balance, and it would melt.
It's not completely out of the question, but it looks harder
Right.
than doing it with magnetic fields. But because bear in mind, you have to, for the purposes that we're going to discuss today, not only do you have to hover the sail, you have to hover some non-trivial weight of spacecraft that's attached with it. So with a solar sail, even with kind of turning all the knobs to 11, you're struggling to come up with a design that would hold its own weight.
Right. Unless it was in the solar atmosphere, and then it's got different kinds of problems.
Well, actually, that doesn't help. The photon flux from the sun and the gravity from the sun both fall off at inverse square. So if you have a good enough performing solar sail to hover in close to the sun, it will also hover when you're distant from the sun.
Oh, interesting. Right.
But when you're close to the sun, it gets hotter. So your choice of materials is more restricted.
Right. Okay. So you've got some kind of electromagnetic sail that is hovering in space, accelerated away from the sun by the solar wind, balancing the gravity that's pulling it inward. What kind of a satellite spacecraft would it be?
Well, the name of the game that led me down this investigation is interstellar travel.
Yeah.
And interstellar travel, as I think we all know, is primarily an energy problem. You know, if you want to move at some reasonable fraction of the speed of light, your kinetic energy in the spacecraft per unit mass is really, really high. The energy has to come from somewhere. If it comes from something you have to build, that gets expensive. So the name of the game is, where can you find lots of energy that you can channel into the spacecraft cheaply? And, cheap beams is how I characterize that problem. And what we found in the course of this paper that we recently got published is that if you get sufficiently close to the sun, there's a well-known technology called thermionic converters. Thermionic converters are essentially they're analogous to like a steam engine or a heat engine. Where you boil something and then convert it to work and condense the something. Only in a thermionic converter, what you're doing is boiling off electrons from one piece of metal. The electrons cross the gap and they condense or are collected by the other piece of metal. And so your work comes out in the form of electricity. And these have been a lot of work's gone on with these over the last 50, 60 years, with the idea being that you would use them as solid state converters for nuclear reactors, or that you would use them with concentrating mirrors as an alternative form of conversion for solar power, because you have to get them quite hot before you materially boil off enough electrons to carry a useful amount of current. So normally the problem is, how do you concentrate enough energy into this little tiny piece of thermionic converter to get it to work?
So for most applications, solar panels are the way to go. But if you can actually get into an environment where you can get that kind of heat and temperature in a concentrated area, these become
attractive. And
compared to acres of solar panels.
Well, solar panels just wouldn't work that close to the sun, right? Solar panels need to be kept in a range where semiconductors work, which is room temperature plus a little bit. So in all space power, the name of the game is not really on the hot side. The name of the game is on the cold side. How do you reject the waste heat? And it's that radiator that normally dominates the mass of some kind of space power supply system. So the nice thing about thermionic converters is, because they work at such high temperatures, the waste heat can come out at a really high temperature too. And so if you pick your distance right, the rate of collection and the rate of radiation just balance each other, and the whole converter just becomes two sheets of metal with a spacer in between.
Wow, that's really interesting. It's funny. Yeah, most people don't realize, they think about collecting power in space, that it's about the solar panels. But a lot of the case, especially if you're near Earth orbit, it's about the radiation. It's about getting rid of the heat, because, as you said, you want your panels to be cooler than the hundreds of degrees that they want to get to in low Earth orbit.
Right, and what
that's
makes
a tricky challenge.
what makes solar panels a convenient form of power collection at around Earth's distance from the sun is that the solar equilibrium temperature, the black body equilibrium temperature of solar radiation, is kind of about room temperature. By no coincidence, right? All the technologies that we've built up are kind of optimized for use at about 1 astronomical unit from the sun, where the Earth is. If we grew up on Venus, maybe we'd have a different technology suite, but that's what we got. So what makes solar panels so simple to use is that they radiate their own waste heat through their backsides. But that doesn't work if you try to crank up the temperature. If you crank up the intensity like tenfold, now you have to somehow mount each little piece of solar cell to a giant radiator. This is what's done in solar concentrator systems on the Earth. You have this big collection lens focusing down on the small solar cell. Great, you saved a lot of solar cell area, which is then attached to a giant aluminum heatsink. So you haven't actually saved anything in terms of power per unit area.
Right. And it's interesting, though. I mean, this whole path of technology would only work and be useful in the most extreme environments, but being close to the sun is one of them. Okay, so you've got this.
And then conversely, the reason for going through all this exercise is if you want to collect a lot of power, and you don't want to have, trillions of dollars of infrastructure in space doing it, you have to go somewhere where a modest amount of mass of spacecraft can collect a lot of power, and close to the sun, that looks like it's a doable thing.
Right. It's one step away from plugging a extension cord into the sun.
Yeah. Go where the power is cheap.
Yeah, exactly. Yeah. Okay, so we've got this spacecraft. It is hovering close to the sun. It is producing enormous amounts of electricity. So let's talk about the other part of this equation, which is what is required to get a spacecraft to interstellar velocities.
So, I'm tempted to say ridiculous amount of energy requirement, right?
I think it's fair.
If you're going at, say, 10% of the speed of light, right, kinetic energy goes as velocity squared. So your kinetic energy is on the order of, I'm missing a factor of 2 here, but is on the order of 1% of the mass of your spacecraft converted to energy. So another way of saying it is, if your spacecraft were entirely made up of fusion bombs and it had no dry mass in it other than the mass of the bombs, you still couldn't get to 10% of the speed of light. It's just too much energy. So it's all this idea and some of the other ideas that I've published and some of the ideas that other people have been publishing in the last 10, 15 years are really all about how do you either send energy to the spacecraft from some outside source, or how do you collect energy on the way, so that you don't have to carry it all with you, because this carry it all with you just doesn't work. And it's a frustrating thing, because you see people publish these naive articles about, well, we'll never get to the stars because, you run the rocket equation and it doesn't work. And, I just want to reach through the screen when I read these articles and shake the author and go, maybe you shouldn't use a rocket.
Yes. Yeah.
It's not like there aren't alternatives.
The entire mass of the universe using a chemical rocket or an ion engine to get you 1% the speed of light.
Yes, which is you could have saved the whole article and said, using chemical rockets for interstellar travel is a stupid idea.
Yes.
Now, on to the real discussion.
Right. But really, we're down to, when you think about the viable technology and even the harvesting hydrogen as you're traveling through the interstellar medium and using that, for your Bussard ramjet, the calculations that I've seen get you a ram scoop that is 1 AU in length. Like there
Well,
are some serious
ram scoops don't work. At
right.
least not with any of the configurations that anybody has dreamed up yet. You know, and a magnetic ram scoop fundamentally can't work for very fundamental reasons that you know, as I like to say, magnetic fields don't collect things, they scatter things. So a lot of the work that I'm interested in that's gone on in the last I say 6 or 8 years now is, okay, maybe we should use that. Maybe we should use the fact that magnetic fields scatter things. And, you know, the magnetic sail that we've been talking about for the statite is exactly that. If you scatter things, you get drag. Drag is useful. You know, you can do things with that.
Slowing down.
It's useful for slowing down, and also any drag device that you can modulate, that you can make bigger and smaller and move, is a windmill in disguise.
Right.
Or if you apply power to it, any drag device that you can push through the medium is a propeller in disguise. So the drag devices are the beginning of a very broad field of inquiry. And over the last few years, you know, I and other people in the business have found ways to do propulsion by using that wind energy to push reaction mass out the spacecraft, or to soar to get the effect of lift over drag by collecting wind energy in one direction and pushing on the wind in another direction, and which just leads to all kinds of useful tricks. So it's quite a broad class of interesting applications.
Yeah, one of the most popular interviews that I've done on this channel is with Andrew Higgins, who is one of your often collaborators, and he is suggesting that idea of using that dynamic soaring to take advantage of those differences of speeds and velocity and all that kind of stuff as a way to accelerate. But sort of back to where I was going, like, either if you want to carry fuel on board, antimatter is about your only choice. And there are downsides of carrying antimatter, both generating and trying to maintain it. But the other method, as you mentioned, is the beamed way.
Okay, so beam,
and this is what's being pitched by the Breakthrough Starshot Foundation. Yes. So what is being beamed?
Okay, so beams can carry beams again are a large class of inquiry. It's not like one thing. And you can beam energy or momentum, right? Of course, if you carry momentum, there's a little bit of energy along for the ride. So it's a question of degree. You know, a stream of pellets being pushed out from the solar system is a beam of sorts. And that's one perfectly good propulsion method that needs more work done on it.
Or those tiny fusion bombs.
Well, maybe, but you don't even necessarily need them. You know, if you can, there are other ways of launching that kind of material. If you want to beam energy, the classical way of doing it is with electromagnetic waves. You know, either laser beams or microwave beams or something like that. And that's been looked at. I mean, if you read between the lines, that goes back to Tsiolkovsky. Although he didn't know what a laser was, but you know, the solar sails are effectively a way of using that same thing, the light pressure coming out from the sun, as a source of momentum. There's nothing wrong with that strategy, except that I'm always looking for the cheap solution, because I want something that will scale up to large robotic probes, or even maybe someday human carrying vehicles. And you know, lasers cost a lot of money per watt, and it takes a lot of watts. And remember, what you want on the spacecraft isn't watts; it's joules, watt seconds. You know, so the other problem is you need a long range you wish a long range out of your beam, because the more time you stay in the beam, the less power it has to have, and the cost of a beam tends to scale rather strongly with the power. So the laser type of approach that people are looking at for very early interstellar probes is targeted for extremely high power for a very short time to push an extremely small object. on the order of grams. And I hope that that program continues to go forward. I'm an all of the above guy in interstellar stuff, but it does have these scaling issues, and the capital cost of the beam is likely to be quite high. And remains to be seen whether that's a check anybody's willing to write. Microwaves are cheaper by the watt, but the range is much, much shorter. So you need more watts. So it kind of comes out in the wash as far as one being as good as the other. And there are various schemes in the literature for using space-based structures to focus those that go back to Bob Forward. But they require very large pieces of in-space infrastructure, which we are not, likely to have next Tuesday.
Right. And the security concerns. I mean, who would feel comfortable with a petawatt laser orbiting overhead?
Yeah, I mean, all problems have solutions, but
the far side of the moon.
We learn to live with a lot of dangerous things over the years. But yeah, it's certainly not a factor to dismiss without thought. The work that is in the paper that we just published, me and my collaborator Garrett, is maybe we should go back and look at charged particles as a means of beaming energy around. Now that's like, you read on most paper on beamed energy going back 40 years, there'll be like a sentence that says, well, you could use charged particles, but they'd spread out, so that's not useful. And this paper kind of came to be when Garrett, who's a particle physics guy, was saying, gee, did you think about the fact that these beams can self-confine because they carry current? If they carry current, they make a magnetic field. The magnetic field tends to confine the beam. And this is a well-known trick. Accelerator physicists do this all the time, sending beams through vacuum chambers. They don't blow up.
Don't black holes know this trick?
Black holes have other means of confining things.
Right. But they create jets. I mean, they use magnetic fields.
And relativistic jets that we see out in the cosmos, span distances ranging from light years to literally hundreds of thousands of light years. And closer to home, although it's not a jet, it's a sheet, right? The solar wind carries a current away from the sun, and that current flows more or less in the plane of the ecliptic, and then it comes back and the circuit is closed at the poles of the sun. Well, that interplanetary current sheet runs all the way from the sun to the edge of the solar system, and it's about 10,000 kilometers thick, which is tiny on the scale of the solar system. It's like a sheet of paper on a scale model of the solar system, and that's confined by its own pinch in exactly the same manner as we were discussing today or in the paper. So this is not, and you've probably heard of Z-pinch for fusion confinement, which is the same thing, or a Coke can crusher. You run a current, down the axis of some system. It makes a magnetic field. The magnetic field tends to squish the thing, the physics of all this gets a little bit complicated because you're talking about a relatively delicate balance of forces. It doesn't work in a pure vacuum. You need the background space plasma to participate because you need a little bit of extra pinch above what you get from the self field of the beam. And that little bit of extra pinch comes from the charge of the beam, the electrons, in this case, the electron beam, repels the electrons in the background space plasma, like charges repel. That leaves a little channel of excess ions that are in the background space plasma. And that little channel looks like a little tiny current in the frame of reference of the electrons going down the beam. But you're running these electrons at essentially close to the speed of light. So that little tiny current has big effects because it's from the point of view of the electrons again, it's a little tiny current coming at you at almost the speed of light. So it adds up to a significant magnetic field in that frame of reference. And I would be remiss not to point out, I mean, this work is not done, right? The whole point of this paper is to basically say that the 40-year kind of naive dismissal of, well, you couldn't use charged particles because their mutual repulsion would blow the beam up, is to say that the picture is more complicated than that. There might be something here. But anytime you're talking about long-range propagation of beams or plasma physics, there's all kinds of potential instabilities. You know, collective waves can build up. Those could disrupt the beam. You know, in no sense have we said we have done all the analysis of every possible mode. We know that that can happen. We're not saying that. What we're saying is we've checked the obvious things that are known in accelerator physics. The obvious things look actually quite promising. That probably means it's meritorious of further investigation, so we can start looking at some of the less obvious things.
Yeah, I mean, I think with a lot of this kinds of stuff, because you have these natural inspirations out there in the universe, you know it's not impossible. Like nuclear fusion, people always laugh about fusion being 30 years away, but there is a source of inspiration right there in the sky saying, you'll get there. Like, because one day you'll figure this out. If you have to gather together a solar mass worth of hydrogen to make the trick work, then that'll be the path. And the same thing.
Well, we've made fusion work without the whole mass of the sun. It just comes in inconveniently high instantaneous power in the form of fusion bombs.
Yeah, right. Well, of course. So all I'm saying is that if you want to, you want something that is useful for baseload power, all you've got to do is gather together a solar mass, and you'll make fusion work. And same thing. All you need to do is bring together 1 billion times the mass of the sun into a concentrated area, get a black hole forming, feed it, you get high velocity jets moving at relativistic speeds. So is there a simpler way, a way that humans can engineer? So
well, maybe we can run an extension cord to the sun. That would be one way of doing it. Or instead of making the sun on the Earth, we could effectively move the sun closer to the Earth as far as power delivery is concerned. Or
put our interstellar spacecraft at the maw of a supermassive black hole that's accelerating relativistic jets.
Those are there doesn't seem to be one of those lying around conveniently close to home.
Yeah, not that close. But I'm saying, like for a lot of stuff, people are just wandering in the wilderness and they don't know if this kind of technology is even out there. And yet, I think the universe shows us with gravitational lenses and relativistic jets and all this kind of stuff that all this physics is going on. It even figured out lasers.
There's a reason for optimism that charged particle beams can in principle be used for carrying power over long distances. Now we have a lot of work to do.
Yeah. So then let's talk about this. So you're gathering up this power, you are turning it into a charged beam of electrons, and you are firing these at relativistic velocities towards your spacecraft. What kind of a distance do you think you can still receive an acceleration from the beam at?
On paper, the numbers look good for confinement over a distance of about 1,000 astronomical units, which is a nice long runway to be pulling power on. Another factor that is always important in looking at interstellar transport is the specific power of the machinery, because you need reasonable acceleration over that distance, over that time, to pick up a useful amount of velocity.
And that feels like a much longer runway than the kinds of runways I've heard proposed for things like Breakthrough Starshot. You don't get that coherent beam holding on target, and you get sort of instantaneous high acceleration, the kind that you're gonna, if you did want to send living creatures, they'd just be turned into goo.
I'm not sure you could send a cell at the accelerations that they're envisioning.
Millions of G's of acceleration and such.
Yeah. No, it's about 10. It's about 10 to the fourth, 10,000 times longer distance than we're talking about with something like Breakthrough Starshot. So that correspondingly results in either a dramatic lowering of the power of the beam required, or for a comparable power beam, a dramatic increase in the mass of the spacecraft that you can send. So the spacecraft that interest me personally tend to have what I call luxuries, like power supplies, and communications and equipment, and maybe a telescope and things like that you'd like to have on an interstellar probe that are hard to package in a gram or two.
So I think people are very familiar with the Breakthrough Starshot class of probe. They're a couple of meters across solar sail with a microscopic
computer
spacecraft,
chip, essentially.
A computer chip. Yeah. What would the kinds of payload, what would the spacecraft look like? The one that you would be accelerating with this
something method? More like New Horizons or Voyager. Something with a power supply that will carry you through the cruise so you can do science along the way. Because if you ever think somebody's going to pay for these things, they're probably not going to pay for it in the hopes of one piece of data arriving in 40 years. They're probably going to want a science team doing things, which means you need a bit rate for your communication system, which means it has to have a power supply to send that scientific data back. I would really like to send probes that go into orbit around the target star, and have years of observation in that solar system, which means you need to put a drag device on the spacecraft so it can slow down when it gets there. Otherwise, you just fly through the target solar system at 10% of the speed of light, and you have an hour to do your observations, and that's the entire career of the spacecraft. It's with traditional funding mechanisms, it's hard to see how a mission like that would get funded, which is why they're not looking at traditional funding mechanisms. They're approaching, philanthropic billionaires. But if you were to think that a national science agency or space agency were going to fund something like that, they're not going to fund it, send everybody home, and then hire a whole new team in 40 years that's going to work for an hour to come back and do the spacecraft. There's got to be some kind of keep alive team, and they have to have science to do so that they want to work on the thing. And that's just part of the mechanism of how these kinds of missions get funded, is they don't just get funded with the Hail Mary pass at the end. Science is an industry of sorts. There has to be a production line that keeps the team that makes the science employed. And so I think those kinds of features are important. And that's why I spend time thinking about how do we get the cost of those missions down so that they are in the Voyager class of funding required. So that you could say, well, we funded Voyager and we're probably glad we did. In modern dollars, it was a few $1 billion mission, but we continue to be using that data stream 40 years later. That sounds like the kind of mission to be worth doing.
So let's talk about the receiver, because what is the actual apparatus that's going to be on the spacecraft that's going to be receiving this beam of charged particles?
And then a miracle occurs. That is absolutely the part that needs the most work. I can't tell you. I can point the way to some ideas for where I think it's a promising avenue of inquiry. The key again is you have to keep the specific power of the receiver high, because you're trying to receive all this power and you don't want the mass of the receiver to be so large you don't get your acceleration. And again, we talked about how the name of the game in high power space systems is how do you reject your heat. So there can't be very much heat to reject. Otherwise, it'll just melt. So what that suggests to I and my co-author is it's not important if you collect 100% of the energy of the beam. What's important is what fraction hits you that you have to get rid of. And you want that fraction to be really low. So if you look right now in the particle accelerator world, there's a lot of work going on what's called Wakefield accelerators, where what you do is you fire a laser beam into a plasma, which stands up a set of electric and magnetic fields in the plasma, which in turn accelerate charged particles, which is what you're interested in doing. We think that mechanism can be run in reverse, where you fire the beam of charged particles into the plasma in the receiver. It sets up waves in the plasma in the receiver, and the waves push the plasma out the back of the receiver, which essentially fires it out as your reaction mass, giving you your rocket. Have we drawn one of those? No. Can I tell you exactly how to build one of those? No.
Right. But that requires propellant, right? That requires something that you're going to be.
This is an energy beam, not a momentum beam. So you're providing energy to expel reaction mass. But when you're talking about reactions taking place with electric fields in charged particles and plasmas, it's just a question of how many nines are there on 99999 times the speed of light. It's not a question of can you achieve high velocities. It's a question of do you have the energy?
Right. So in this scenario, you are, as you said, it is a transfer of energy, not a transfer of momentum. So you are firing these electrons. The spacecraft is receiving these electrons, turning them into electricity,
slowing them down as they pass, and converting that energy into some expelling reaction mass.
Right. You're using that as electricity. You're then expelling a reaction mass, like an ion engine, say,
well, an ion engine in the most abstract sense, yes.
But you are hurling particles overboard.
Yes.
The way an ion engine does. The way, obviously like a chemical rocket, but an ion engine is a sort of closer analogy because it's using electricity to throw out the reaction mass.
Right. But I think the reason why I said it's only kind of like it is you have to skip those conversion steps. If you received it as electricity and then use that electricity to drive some kind of accelerator, the waste heat would kill you. So instead you have to directly convert the deceleration of the electrons into the acceleration of the plasma going backwards.
Right. So they don't even have time to be turned into electricity. They're putting straight to work as an accelerant for your propellant. Okay. Right. So why can't it be a transfer of momentum?
Well, it can be, but it's incredibly wasteful to do that. Electrons moving, there's this relativistic parameter called gamma, which is like, what's the effective mass? I hate using the word effective mass. It's a measure of how many times, it's indirectly related to how many times the speed of light you're going. Right. As gamma, when gamma is equal to 1, your kinetic energy is equal to your rest mass energy. Right. If you converted you have so much kinetic energy that if you converted all the mass to energy, those numbers will be the same. We're talking about beams that have gamma of 100 or more. So the kinetic energy is very large compared to the mass energy. But the momentum, so what that effectively means is when you're talking about particles, whatever they are, that are gamma of 100 or more, the energy to momentum is about the same as it is for light. Because it's almost all energy. It's almost no rest mass. So you'd have to be back into breakthrough starshot like power is to accelerate grams. It's if you want to accelerate and you're paying attention to what things cost, you'd like your exhaust velocity to be kind of on the same magnitude as the velocity you're trying to achieve. That way that's what minimizes the power required. So it could be done, but even my imagination boggles at scaling up the power by 10 to the 5th.
Well, I mean, the reason I was wondering, because this is essentially the same thing that's holding your statite in position, is you're using you're reacting with electricity with the solar wind, and then you're sending this beam of particles. You would want to then potentially react with that beam of particles in a similar fashion, but you're saying that it's just not efficient. You're orders of 5 orders of magnitude off from what you need.
Yeah,
right.
You'd need, okay. So to be less colloquial, What you'd need is a charged particle sail, like a mag sail or an e-sail. It would need to be very stiff. Because the electrons are moving so close to the speed of light, you'd need an extremely strong magnetic field to do the deflection in a reasonable amount of distance. Because what's called the rigidity, the distance magnetic field product that it takes to turn this beam is quite fierce, because it's going so close to the speed of light. In principle, could be done. If you wanted to pursue that approach, what you would really like to do is use a slower beam. Then, rather than putting in 99 times the energy of the particle into its kinetic energy, you'd like to fire a beam that's going like 20 or 30% of the speed of light, and reflect that, and that would match, kind of impedance match, what's going on with the beam with what's going on with the spacecraft. The problem is the equations for what it takes to do this pinch, this long-range confinement of the beam, favor going to high gamma, high fractions of the speed of light. So we say in the paper, we are not ruling out that you could use these tricks to make it work with a heavier charged particle beam, but the analysis, you'd be in a regime where the scaling is not so favorable. It looked harder, and we had enough miracles to pull off, so we wanted to start with the easiest possible case.
But if I understand correctly, the advantage of using that mag sail or electric sail when you're at velocity is your braking mechanism, that you're interacting with the interstellar medium, and that is slowing you down to be able to go into orbit around your target.
It's the same technology. It mightn't be the same piece of hardware, because the math on what it takes to deflect a large area of very weak wind and what it takes to deflect a small area of very high intensity beam are not necessarily going to give you the same piece of hardware on both ends of the system, but it's the same principles that apply. If there's time, we can talk about some stuff that's kind of current work, which is sending a stream of macroscopic particles, little pellets, at 2% of the speed of light, and then bouncing those off of this kind of a sail as an inexpensive way to get to velocities that are more down in the 2% of the speed of light range.
Right.
But
that's hundreds of years to get to Alpha Centauri.
Well, but almost every way I know of to get to velocities that I call interesting, at prices I call affordable, for interstellar flight, involves a multi-stage accelerator. It's not one engine does it all. So don't despise getting the first 2% of this light for cheap.
Well, I mean, we're already sending the Voyagers on an interstellar mission. It's just going to take 50,000 years to reach. So if we're patient, when our robot bodies show up, we can watch them arrive at some distant
I'm not
target.
patient, and funding agencies aren't patient either.
But think of that. The thousands of years of science, it just keeps rolling in year after year after year.
We're going to die soon. But that's not what I was getting to. I wasn't getting. I don't actually have a lot of patience with the. We'll just be patient, because no one will ever fund the mission for which you just be patient. Money has a time value. But what I'm saying is, just like we need multi-stage chemical rockets to do things from Earth to other places in the solar system, an interstellar mission almost certainly involves multiple stages of accelerator. For example, right, this is all stuff that's been published before alone or with other collaborators like Andrew, right? If you can get the first 2% of light speed by dynamic soaring in the heliopause, you can send a stream of pellets away from the sun with sunlight pressure and use what we call wind pellet shear sailing to get from 2% of the speed of light to 8% of the speed of light. And you can use the windmill powered rocket we talked about earlier to get from 8% of the speed of light to 24% of the speed of light. Okay, so that's 3 stages of acceleration, and 24% of the speed of light is not a velocity to be despised in interstellar flight. You know, that's a credible trip time for a robotic probe to Alpha Centauri. So that's why I every one of those stages is interesting, right? You need each one of them. The later ones require the velocity from the earlier ones to do their job. So cheap 2% of speed of light is something I'll buy right now.
but that sounds like a really exciting part of a science fiction movie where they're moving through the various stages of interstellar transportation, and maybe the antimatter drive kicks in at the end. I love that. I love that idea. I've never actually heard someone proposing a multi-stage system.
I don't
as an
understand.
interstellar probe.
I didn't either when I first put it down, and I don't understand why. It's not like staging is some new idea. Okay, Tsiolkovsky came up with that one too. So
right, and that different forms of propellant are going to work in different regimes depending on your distance from the star, depending on the mass of your spacecraft, depending on what's available to you in the interstellar environment. That's really interesting. I like that idea, and it of course, like now that you say it, of course that whatever someone in the end is going to put together all the different pieces in whatever are the natural ratios to get you the most interstellar velocity you can get your hands on.
Similarly, you obviously slow down at the end with some kind of drag device. We don't send probes to Mars and then do a reverse burn with all the chemical rockets that it takes to slow down to get there. We don't double the cost of the mission because there's almost always a way to shed velocity that's easier than it is to acquire it. And so I just boggle when I read these articles about, and I don't just mean articles, when I read studies from organizations like JPL. I've been at interstellar conferences where the JPL people get up and say, well, what we really like to do is slow down, but now that doubles the delta V of the mission, which exponentially increases the cost. And it's like, then don't do it that way.
Right. There are some tricks. There are some ways you can shed velocity. Yeah. Okay. So put it all together for me then. Imagine we are, 50 years into the future, and the large technical challenges have been sorted, and humanity begins the process of building this mission. So what happens?
So first you launch, for this particular technology, I could spin a story like this 3 or 4 different ways now, but for this particular technology, and I'll note in passing, part of the reason I keep working on this is as a systems engineer or a program manager, my rule is if I have a really hard problem to solve, I have to have 3 different ways of solving it before I can take for granted that at least one of them is going to work. So we're trying to invent multiple different ways of solving all these problems so that we can be reasonably confident at least one of them was going to work. Yeah.
But I want the movie montage.
Okay, the movie montage.
Right.
You start by launching the statite. It has to get down to close to the sun. That will probably involve an electric propulsion system like an ion thruster, because it takes a lot of delta V to get close to the sun, but you're not in a great big hurry to do it. It goes down close to the sun and takes up station at a point where the sun, the statite, and Alpha Centauri are all in a line. Then you launch your spacecraft, which has, as we were discussing, a multiplicity of propulsion systems on it. The first one of which, in this case, is the receiver for converting the electron beam into rocket thrust and a big tank of propellant. It gets into the beam. You turn the beam on, and we start expelling reaction mass, and you start accelerating. And you keep accelerating, and in your movie montage, it's like running the old Star Trek Next Generation credit scene. You fly by Mars, you fly by Jupiter, you fly by Saturn, you fly by the outer gas giants, and you fly by every planet in the solar system, and you're now 5% of the way through your acceleration distance. You keep going.
And how long is this taking? I mean, to reach 1,000 AU.
That depends on the acceleration.
No,
it's months.
Yeah. Okay.
You stay in the beam for months to pick up your acceleration velocity,
Right.
and depending on the parameters of your system, you finish. Ideally, from my point of view, we'd be able to get you up to about 8% of the speed of light, where you kick on the windmill-powered rocket, which gets you from 8% of the speed of light to 24% of the speed of light, and then you coast for 20 years or so, and then you start braking. You have to brake before you get to Alpha Centauri, because at these speeds, solar systems are very small objects. At a quarter of the speed of light, the sun to Pluto is a matter of like a day. So you really don't have time to wait to get to the target solar system before you slow down. You have to brake against the interstellar medium, which you do with electric or magnetic sails. It takes probably on the order of a year to slow down to the point where you could do some kind of orbital insertion around the star of Alpha or Proxima Centauri. And then once you're in stellar orbit, you use some other more conventional form of propulsion to get into the neighborhood of the planet that you want to take pictures of.
Right. So there's a couple of things that I know people are going to post in the comments right now, and they're going to say, that's ridiculous. You're traveling at 25% the speed of light, 24% the speed of light. Even the smallest grain of interstellar dust is going to destroy your spacecraft. And Andrew Higgins has patiently debunked this in the comments of the video that we did, where he's like, we've done these experiments and they're fine, that you get sandblasting, like with the actual particles, the interstellar particles, the protons that you're hitting, is like this slight sheen. You're going to lose a millimeter over the entire duration of your journey. And the larger ones are so rare, and actually the amount of joules that are transferred is very low. So do you feel comfortable in that you're not going to receive a catastrophic impact when you're traveling at 24% the speed of light?
Okay. I don't lose sleep over it.
Okay. Yeah.
But comfortable isn't the word I would use. If the interstellar medium has the properties that we think it does, then you do have to take it into account. Passive shields of reasonable mass appear up to the task if the medium has the properties we currently think it does. But we know much less about the interstellar medium than we would like to think that we do. We really, really, really would like to get some precursor missions out there to directly sample what's going on. I mean, Voyagers have only gone like 130, 140 AU. Alpha Centauri isn't even in the same gas cloud as the solar system. It's in what's called the G cloud. What's the dust population in our local interstellar cloud? We don't really know. What's the dust population like in the G cloud? We don't really know. But on the other hand, if there were enough grain of sand sized pieces of dust to be a hazard to navigation, that too has engineering solutions. They're just different engineering solutions. So the reason why you really need a precursor mission is not to tell you if it's possible. It's to measure the engineering parameters you need to design the spacecraft to stand up to the environment.
Right. So for the person who's watching this, and this is the objection that has popped into your brain, one, Jeff has thought of this, right? This has occurred to you that this may be a problem.
And many other people. There's the whole literature on interstellar dust impacts. Yes.
And people have both fired beams of protons at various kinds of spaceship metal to see what the effect is going to be, and also calculated the impacts of larger pieces of sand and dust, and calculated what kinds of ablative surfaces would be required to deal with that. And the question is how much of it is out there, and that's why a precursor mission, an interstellar mission, would be wonderful to tell us what's out there. So
particularly, it's the tail that we don't know. Right, we can remotely measure the gas. We can remotely measure a little bit that tells us something about the fine dust, but you can't really remotely measure the grains of sand. Um, uh, and I personally believe, with no data whatsoever, because nobody has any data, that there probably is a population of grains of sand that might be something that we have to take into account in the design of the spacecraft, because we haven't sampled anything. We don't, and we're just saying we never measured anything, so we don't know that there's anything like that out there. But we've recently been discovering there's quite a population of interstellar objects. We've had 2 interstellar comets fall into the solar system. We've seen in the 20 or 30 light years away from the sun, we've seen small rogue planets that are wandering free, not attached to a star. And my logic is, well, if there's gas and there's dust and there's snowballs and there's planets, there's probably stuff in between. But if the worst happened, right, and it turned out that the grain of dust the grain of sand population, grain of sand at these speeds really is a problem. It's going to punch through a reasonable shield. What you do is carry an active defense. You'd have a high power pulse laser. You'd shine a laser beam in front of the spacecraft. When you saw the sparkle that told you that, something was in the line of the beam, which means it's actually right in front of you and it's going to hit you, you turn up the power and zap it before it got to you. That would take weight. That would take power. It would be a design consideration of the spacecraft. Like an analogy is, we also don't know as much as we'd like to about the hazards of galactic cosmic radiation for interplanetary travel for humans in the solar system. But we've got 3 or 4 ways of solving the problem. It'd be great to know more about it, because that would tell you which the 3 or 4 ways you should design your missions around. But it's not like you sit there going, we can never go to Mars because there's such a thing as cosmic radiation. It's like, yeah, we know. We've thought of that. We're asking the question of which of the engineering solutions is the right one to apply to the problem.
And once again, the Earth is showing us 2 of them, which is use a magnetic field and you use protons
Your passive
of
mass,
atmosphere.
Yes.
And there's 2 ways the Earth has figured out to deal with galactic cosmic radiation. Can we engineer something without having to take an entire Earth with us? Maybe.
Yes.
We'll find out. Okay, so that's the big one. And so hopefully people who are watching this and they're angrily typing comments right now are going to just back away for a second and ponder that this has been thought through. Man, I've seen things. So then the other thing is that people are going to be saying, well, this is ridiculous. Humans are never going to be able to travel to another star system. So just to clarify, we're talking mainly about robots, but you do hold hope that this kind of technology could scale eventually to carry, if not people, then maybe, I don't know, DNA printers that will set up biospheres on other uninhabited worlds, things like that.
Okay, so I'm just trying. We could do an hour on this one.
We don't have an hour.
For reasons that would take a paper to discuss, the interesting voyage length is kind of in the 4 to 8 to 12 light year distance range. If you can do voyages like that, and if you can carry outposts of human civilization over distances like that, colonizing the galaxy is just a matter of time. Because even if it takes 200 years for the civilization you set up after an 8 or 12 light year jump, to be able to send out their own spacecraft in an eye blink, you've filled the galaxy. What's called the percolation model of spaceflight. So the important thing is not to be able to do very, very long voyages, is to be able to do these shorter voyages with people. Are we there yet with 25% of the speed of light? No. 25% of the speed of light gets you a 1 generation ship to something like Alpha Centauri or some other nearby Bernard star or some nearby target. we'd have to get up to like 40 or 50% of the speed of light to be able to do these 8 to 12 light year kinds of hops. We're also not done working. We're just getting started. You know, when I first was reading about this field, it was Bussard ramjets or nothing, and Bussard ramjets don't work. Okay. In the last 20 years, with almost entirely part-time efforts of people who don't get paid for this stuff, you know, we now have a collection, an armamentarium building up of strategies that if you put them together could get you potentially affordably, you know, to 20, 25% of the speed of light, you know, for like $1 billion of launch cost for a spacecraft the size of Voyager or New Horizons. Okay, that's an Apollo program cost for a 20 or 30 person human carrying habitat. Are we done?
I'm going to propose that you're off by an order. Yeah. I mean, I think you're off by a couple of orders of magnitude, but even if it is 10 times Apollo, to send a mission to another star system feels worth it.
And we're not done. Okay. We haven't exhausted, it's not like we've exhausted all the ideas. If you plot the rate of improvement of our theoretical constructs for how to do a mission like this, it's staggering how much better it's gotten in the last 10 or 20 years on paper. You know, that there's more. I can't tell you every idea we have in the pipeline, but there's more coming. I am confident that by the time that we could launch that first human expedition at a quarter of the speed of light that would take a generation to get to Alpha Centauri, our chances of being able to figure out how to launch something that's twice that fast to get to stars that are twice that far is pretty good.
So place your bets. When do we launch the statite?
That's not a well-posed problem. Sorry, I don't play that game. The reason is that you're asking how long it takes to run when we don't know when we start the race. Whether it be with the statites, or whether it be with the plasma sailing, or whether it be with the pellet stuff that I'm working on now.
Okay. Let me, you know what? We'll go back. Let me rephrase the question. Okay. When does our first spacecraft arrive at? When does our first interstellar spacecraft arrive at its destination? Place your bets.
30 years after we get serious. Well, 30 years after we launch, which is 10 years after we get serious.
Yeah.
Which
so 40 years.
Is sometime between next week or never. Because there's no money. There's no funding to mature these technologies. So you can't put a clock on it because we haven't started.
Sure. But there is like a rising tide lift all boats, that there is like underlying base technology that's developed for various things. The way I describe it, people always ask me, like, when will Breakthrough Starshot be launched towards another star system? And my answer to that is within a few decades after Breakthrough Starshot is used to explore the solar system. That there is a feeling that you'll have when we have become serious. And so, 40 years when someone goes, I'm serious, let's, we choose to go to Alpha Centauri in this century, not because it's easy, but because it's hard. So what will the rising tide feel like when we know that we're starting to approach someone making this a priority? What's it going to feel like in terms of our exploration, our access to the solar system as a precursor?
Okay. Again, this is a long topic that I'm attempting to compress.
I'll direct people to the forthcoming paper.
No, I've done speeches on space policy and how we manage technology. It's a long topic, but people on the street have this subconscious impression that we have people, agencies. People are in white coats staring at computer screens, in darkened rooms, working on these problems. Like Indiana Jones, top men are off working on these problems. It's not true, right? There is no current customer base that desires to pay for faster or less expensive transportation through the solar system. So it's exactly like asking Robert Goddard how long it's going to take to get to the moon, right? It's because, well, once you've mapped out that there's a path to solve the problems, which is the work that I and others are undertaking now, there's this unknowable incubation time of how long is it before somebody says, okay, but I want that problem to be solved. Today, there's no customers for advanced space propulsion. People think that that's NASA. That's not true. NASA's well aware of this. They call it the Valley of Death. That there's a trickles of funding for work that you do on the blackboard or on the computer, what they call TRL 1, 2, maybe 3. And once you're like TRL 6, which is I've flown it in space and it works, or I've flown a subscale version of it in space and it looks good, then you can think about being included in some kind of funded mission. But the work in the middle currently has no source of support. So and this is a known problem. I'm not the only one worrying about this. If you ask why that is, it fundamentally comes down to the 1962 decision by Kennedy to make NASA, which was the technology pushing agency, also the mission conducting agency. And there's a conflict of interest when the same agency defines what problems are worth solving and decides what technologies are needed to solve them. Because guess what? If your career is on the line, what you do is you define missions that don't require new technologies to solve.
Yeah, I mean, there are these pockets of this level of innovation, like NIAC and,
which takes
and other
you to
things
TRL
like that.
3, not the TRL 5 or 6.
Right. Yes. Yeah. But I like, for me, the most interesting work that NASA does is in the TRL 1 to TRL 3. That is the technology readiness level.
Yeah.
Just for people who aren't aware of that.
And
that
NIAC is absolutely one of the gems of NASA, and they've sponsored fantastic work. And if people had any, I mean, I think it's the best money NASA spends.
I 100% agree with you. Yeah. Yeah. I would give vastly more money to NIAC and dramatically less money to more established technology.
Well, but what's missing, where this Valley of Death lies, is if you go back to the aviation era, it's in the X-planes, right? It's NACA funded exactly this kind of work for aircraft. How do we take these ideas from the promising thing that looks good on paper, or the promising idea that looks good in the lab, to the point where an aircraft manufacturer would take the risk of including it into a design of an aircraft? And maybe that's by testing it in a proper ground facility. Maybe that's by building a new wind tunnel. Maybe that's by building an experimental aircraft to try these ideas out. That's the class of challenge that we face in spaceflight today that currently in the West doesn't have a mechanism for the funding. I think what will happen is sooner or later, and this is the thing that nobody can say how long is sooner or later, right? Sooner or later, either competitive pressures or military applications will arise, just as they have done in these arenas in the past, where now there is an interest group, not just in studying the problems, but in solving them. And when that happens, progress could become very rapid, but we don't know when that's going to happen.
I mean, my dream NASA is the one that's obsessed at lowering risk. That is lowering technical risk. That's it. That they are just waiting for someone to say that something sounds too risky.
The chartered
in terms
purpose
of a technology.
of NASA, the NASA Act of 1958, I'm quoting from memory here, I don't have it in front of me, so I won't get it quite right, is to improve the performance, speed, range, utility, etc., of air and space vehicles. That's why I think we have a NASA. I don't think we have a NASA to plant flags and footprints. I think we, as we used to say in the space advocacy world, it shouldn't be the job of NASA to go to Mars. It should be the job of NASA to make it possible for the National Geographic Society to go to Mars.
I love it. That's awesome. Jeff, what are you obsessed with?
Well, I have a day job, which occupies me, which is also power beaming. In that case, it's a lot closer to home. It's power beaming from the ground to aircraft or spacecraft in flight, so that we can both electrify aviation, so that we can start doing power-rich things on spacecraft without having to carry acres of solar panels, and so that we can fly fast the same way we today fly slow without having tailpipe emissions up in the atmosphere.
Well, I mean, just like imagine an airplane that completes a journey and isn't carrying any fuel on board. It's just receiving.
Not carrying fuel. It doesn't have any exhaust. It just pushes on the atmosphere as you go. Right, it's also the only practical way to have a nuclear-powered airplane. You put the nuclear reactor on the ground, it puts power into the grid, you beam the power into the airplane.
Right.
So that's my day job. As far as interstellar stuff is concerned, I've mentioned a couple of times, what I'm currently working on is this pellet concept again. Renee Heller over in Germany found that if you puff up these little aerographite puffballs really close to the sun, they get pushed away by the photon pressure at about 2% of the speed of light, which is another form of cheap beam. In this case, it's a stream of pellets being pushed along at 2% of the speed of light for the cost of putting a statite close to the sun. And so I am both looking, I'm putting some work into a precursor mission, an Oort cloud mission, where it'd take about 10 years to get out to the Oort cloud, which is thousands of astronomical units away from the sun, not hundreds. We have no idea what's out there other than from telescopic observation, and it's too dark to see anything with a telescope. So we only even know that there is an Oort cloud because we assume comets come from somewhere. So it's a completely unexplored region of space that I think is incredibly scientifically interesting in its own right. And it also would require solving all these precursor problems, and it might provide a scientific reason why we need a 2% of the speed of light flight demonstration. So I'm putting a lot of work into putting the conceptual framework of a mission like that together in the hopes of developing some interest in the scientific community on, hey, if we knew that you could fly a mission like that, we would have asked NASA to put it on the list of missions we'd like to fly.
Fantastic. Well, Jeff, thank you so much for taking the time to chat with me today and explaining this, and good luck with all of your efforts. I hope that one of them gets us closer to traveling to another star system.
Thank you, sir.
I hope you enjoyed that conversation with Jeff Greason. I just was having so much fun. We could have talked all day, and obviously some of the conversations could have turned into papers of their own. And so I'm sure we'll be talking again in the future. Now I want to give you some of my thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Bill, David Giltonen, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modso, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Chiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. One of the biggest takeaways that I had from this conversation was the idea of a multi-stage interstellar rocket. And when Jeff mentioned it, it was obvious. And yet no one had ever talked about it. I've never even really thought about this, that there are different kinds of propulsion systems that will work at different regimes. When you're close to the sun, you've got a lot of energy. One method works best. But then when you're farther from the sun, another propulsion system makes sense and kicks in. And then when you're out in interstellar space, maybe another mechanism is going to kick in, and then a different mechanism for decelerating your spacecraft to arrive at your target. And so when you think about all the different methods of accelerating spacecraft to interstellar velocities, maybe they'll all come together and play a part in sending humanity's first spacecraft to another star system. Now, I referenced another interview that I've done with Andrew Higgins, and it is like required watching. And so if you really enjoyed the vibe and the conversation from this, you're really going to enjoy this interview that I did with Andrew Higgins. All right. We'll see you next time.